Good. Bertrand. Okay, so we start again with the second part of Gaëtan's lecture.
So this morning we saw two operations on cohomology classes. And at the end, what we really want is to count. So we want not classes, but numbers. So if we have a tower of classes like this, and as Vincent was saying, symmetric, you can construct what we will call the partition function, which is encoding the intersection numbers of this with psi classes, which are the most basic classes that we have. So the partition function, it's I can write it as an exponential of a formal series in countably many variable and one parameter h bar. So I will call the variables p0, p1, etc. And we define it in the following way. So I'll always have the stability condition h bar to the g minus 1 over n factorial, and the integral of the class times the psi classes to arbitrary powers. So I have to sum as well over the m's. And I want to store this information, so I'm putting formal variables p m1, p mn in front of this. So I'm not losing anything, it's just a convenient way to consider all these numbers at the same time. And there's many reasons why this is interesting to do it in this way. One is related to integrable systems. It turns out that in a good amount of cases, this is a tau function of an integrable system. But I'm not going to talk at all about that. However, this will still be a convenient tool as an intermediate step before going to topological recursion.
Sorry, the omega could be anything? Or?
Yeah, for the moment, it could be anything. So this depends on the choice of omega. Of course, if you take anything, it's not going to be a tau function. But for well-chosen omega, it's going to be. So what I want to say is, what is the operation of translation and the operation of diffusion doing to this generating series? So if I do z t hat omega, so I choose a formal series t as here. And if you look at what is this, it means that you're adding extra. So what I had here was not this psi k. It was for the remark, it was t hat of psi n plus I. So it means that instead of this, what you actually have is the sum over L integral mgn plus L, these psi classes, and also the extra psi, which come with what? Which come with the coefficients of the formal series T, not anymore with the p's. So it looks like a Taylor series expansion, but at a different point. So this, so like this, is in fact the translation of the formal partition function. So either I write it like this, p plus t hat, so that's why I shouldn't put arrows. And I can also write it as a differential operator, as an operator acting on this, which is just a translation operator. So that explains the name translation. So what about the diffusion?
Sorry, Gaëtan.
Yes?
When you integrate over g of
n.
But you need the total class that you multiply there to have top dimension, right, or something.
So this is what I said at the very beginning. Integral of something is
you
either
don't
the
care.
integral if it's top dimension, it's 0 otherwise.
Ah, okay, so you don't mind. Okay, thank you.
So when you do the diffusion, it's a little application of Feynman diagram expansion or the Wick theorem that it can be written in this way. So P is a bad letter for an index, it's the M, H bar over 2, and then D hat M1, M2, so these are the coefficients of the formal series D hat U1, U2. And here dp m1, dp m2. Applied to z omega. Yes?
What do you mean by your notation p plus t hat?
I mean the collection of variables pm plus t hat m, where my t, these t hat m are the coefficients. In fact, if we wanted, we could say we could go further, apply higher order operators. You would be able to describe it as well. But these are, I would say, the most important one. Okay. And this is why I call it diffusion. I mean, this is a second order differential operator. So we can make a vote at the end of the week if you find a better name, because this is certainly not standard. Let's temporarily I take that. Okay. So maybe you don't recognize why this applied to this is generating these sums over stable graphs. So another way, I would say, if this d hat, which I can consider as a matrix, is invertible, this thing, I mean, everything is a formal series. I'm not worried too much about convergence. But this is the same as Gaussian convolution. So here I will put minus 1 over 2 h bar, the inverse matrix, p tilde m1, p tilde m2. And then z omega h bar p plus p tilde. So I'm saying that this thing and these things are the same, at least when d hat is invertible. And let's say it's infinite dimension if you want to make sure everything is well defined. And maybe here it is more one step less to see why is that generating stable graphs. Because you know the Wick theorem. You're going to replace this z by its definition. So it's a full formal series here. And you expand everything out of the exponential. That you consider as weight of the vertices. And computing this moment against the Gaussian measure, some polynomial is going to make you the edges, the pairing. And then you have to worry about where is the h bar and that the h bar behaves in the way that it did. So here, the fact that we have that, this is essentially Wick theorem. And not even the one for matrices, just the one for Gaussian vectors. Okay. So now we're prepared to make the connection with topological recursion. So to start with, I'm going to say what happens for spectral curve with one ramification point. And then I will say a few words about how you generalize the formulas for several ramification points. But this is just more heavy to write, but not really more complicated conceptually. So let's take a spectral curve. And assume that dx has one simple zero, which I'm going to call A. Then I can always take a local coordinate so that x is z squared over 2 plus x of A. So TR is, because the residue formula, it's coordinate-free formulation. You can choose whatever coordinate you prefer. This one turns out to be convenient for the type of thing I want to do. And in case there are more interesting things, we'll see a more global formulation later. So I'm not sure if Bertrand had said, but there's a basis of differential on which you can decompose the omega gn of TR. So here that produces some omega gn. And if I introduce the following basis of differentials, so z equals 0 is the ramification point. I'm going to take the primitive of omega 0, 2. So this is a one form in z. So I'm taking the residue in another variable, z prime. It is here, the z appears here, so it's a one form here, but I integrate this one to get a function of z prime. Here I can start from 0. And here I'm going to put z prime to the 2m plus, I think, 1 or 2. I think I want 2. Okay. So what is that looking like? The fact that omega 02 has a double pole at coinciding point with coefficient 1 is going to tell you that if you try to send z, so where can it have pole? It can only have pole when z approaches the ramification point. And if you try to look what is the local behavior, you're going to see that this is exactly what I put here. But then there's a holomorphic part. So not O of 1, but big O of dz. And so when I take m non-negative, I see differential form that have poles of order at least 2, so there's no residue, no simple pole. And that's indeed true. The omega gn in any variable, they don't have residues at ramification point. The other thing that I'm not sure if Bertrand said is that these omega gn are odd with respect to the involution. Which means if I do this, so here the involution is the holomorphic map on the curve, which is locally defined, and extend the two sheets meeting at the ramification point. And because the local coordinate I chose here is just z goes to minus z. And in fact, one of the topological recursion is really constructed so that it solves certain equations. And one of these equations is telling you that this combination, okay, maybe it's non-zero, but it must be holomorphic at the ramification point. And this is the case here. In fact, if I had put some dz over z to m plus 1, when z goes to minus z, this is even. So the omega gn are not going to have any of those because of this property. So you could say, well, it must decompose on base of differential that have poles which are of even degree. And I exhausted everything here because I just have run ramification point. So using this type of argument, you can show that the omega gn, maybe I write it here, z1, zn, they decompose exactly on those differentials, and there's some numbers which I'm going to call fgn, m1, mn. And because the omega gn are meromorphic forms, it means the order of the poles must be bounded. So also I write here a sum over all non-negative m's. This must actually be finite. And we know that an explicit bound is related to the dimension of the moduli space, and we're going to see somehow that it matches what I'm going to write later. So this is a finite sum. Okay. So if I take a spectral curve, I get a collection of numbers here. And it would just be an equivalent way to repackage that into a generating series as well. So the TR partition function that depends on the spectral curve. It depends on the parameter h bar and some formal parameters q0, q1, etc. It's putting these fg's in the same type of generating series. So here we have this type of generating series. Here we have another one. And what I'm saying is that you can make things match. So this I'm going to erase. But when you want to make things match, I mean, on one side, this takes as input a spectral curve. And this takes as input a collection of classes. So what will happen is that there is, for any spectral curve, you can find a certain class for which there will be some identification of these two partition functions. And if that is true, because, I mean, these store the same information as the omega, the collection of all omega gn. If this is true, then it means that every omega gn for any spectral curve, you can represent it as some intersection numbers for a certain class. And that's some of the purpose of these lectures, to explain that. Good. So it was maybe A. So now we come to, and everything before was just preparation. And here, I mean, there's some, I mean, at some point you have to do something non-trivial. But you have to just do it once. And this is within conjecture proved by Kontsevich, and that's some of the, I mean, there will be a second deep result which I mentioned at the end, but this is really the foundational results for everything here. The rest is, I would say, just algebra and basic facts in geometry. So there's two parts in Witten's conjecture. One part was that this generating series, when you just take the trivial class, so only psi-class intersections, is a tau function of KdV. That's not the part I'm interested in. But there's a second part, which is this thing solves certain constraints, certain differential equations, which are linear, called Virasoro constraints. And that's what I want. So if you take this spectral curve, which probably you worked with in the exercises. So the standard omega 02. Then, in that case, omega 02 is just a standard thing, so let me call that omega 02 standard. And when you have omega 02 standard, here this is just 2m plus 2. So the simplest thing you can imagine. Okay, so it means this omega gen, it's actually a rational function up to dz1, dzn, which has only negative powers. And you look at the coefficients. And what the conjecture is saying, I mean the theorem now is saying, is that these guys are exactly the psi-class integrals. Up to a combinatorial factor, which is 2mi plus 1 double factorial. Okay, so it means that for this specific spectral curve, the two partition functions agree, provided that you relate the q's to the p's. So I would say z, so the class here is just the fundamental class, so 1 instead of omega. And so ztr depend on the spectral curve. So this spectral curve is called the Airy curve. So it's z tr Airy. But so what about this? So let me look. I take z on the fundamental class, I get this psi class, but here I would like to insert some double factorial. Therefore, I need to replace pm with 2m plus 1 double factorial qm. And so that's the deep theorem. And there's one thing nice about this deep theorem that it has many proofs. So the original one was from Kontsevich with a little gap, or let's say things which were not really justified, which were later justified by Zvonkin. But by now, I think there's maybe 4 or 5 different proofs. And there is one which is totally geometric. And you cut the surface in certain ways, and you manage to prove that. So it's really, you compute integrals. So more precisely, the geometric ways to say actually you can find representative in terms of differential form for these classes. And you can then really integrate it on the moduli space. And you can cut things on the moduli space to get a recursion on the topology of the surface with explicit representatives of these guys. So if you want to know about that, we can discuss, but not during the course. And that also explains why you have this combinatorial factor over here. Okay. So I can say this statement is equivalent to the fact that you have some operators that take so any of those because they are the same and kill them, and these are differential operators in the p's or the q's which satisfy Virasoro type commutation relations and which are totally explicit. And these equations are equivalent to topological recursion in the residue form in the way Bertrand showed you. That's a little generating series computation to show these are equivalent. Okay. Good. So now the program is to see what happens when you deform spectral curves. This statement is equivalent to TR computes this, so to this equality. So TR defined in this residue with this residue formula way. Okay. So now let's look at the marginal spectral curve. So I can still always choose my local coordinates so that x is like this. But then y is going to have some expansion. So this expansion, I won't stick to see it as a deformation, so I write minus z plus a full series. And that series may contain a z term as well. It just means that the coefficient here is not -1, it is what I put here, -1. And so here I want to put, well, for the moment let's call that t tilde m z2 m plus 1. And why do I only write odd powers? This is because in topological recursion, in the only way y appears is in the recursion kernel. It's in the denominator, and what you do is 1 over yz minus y, the involution in z. So the involution here is minus z. So you take the odd part of y. So I could add here an even part, but the omega gn are not sensitive at all to that even part. You could set it to 0, you get the same omega gn. And then you have the omega 02. So this one we know it must have a double pole at coinciding point with residue 1. And then it must be holomorphic. And so here I expand everything because TR is a residue computation at the point. So it's enough to know the expansion of your spectral curve near the ramification point. You don't need it elsewhere. So I'm just going to expand when z1, z2 goes to 0. And here we will see, so what I will call d tilde m1, m2, z1 to m1, z2 to m2, dz1, dz2. So here I had my sum over m. Positive plus even part. And so here I write plus a non-odd part. So for omega 02, it's a bit the same. You first, what is really important is the part which in each variable is odd. So z2m times dz, this is odd. And then you could have terms where either z1 or z2 has even terms, or both of them are even. That's what I call non-odd. But this non-odd part, the only place where it shows up is in the expression for the differential. It's going to affect the big O of dz here. Otherwise, it doesn't change the coefficients fgn. So that's all what is going to matter here. Here, it's z1, z2 goes to 0. Only near, I need the expansion near the ramification point. Okay. So if I do that, spectral curve S, that's the most general one locally. The claim, so it's a theorem, is that the TR partition function for this spectral curve is a translation and a diffusion of the Airy spectral curve. Yes? So Z is my local coordinate, so it's going to 0 when the ramification point is A. And I realize here I forgot, so these things always come up with some factors, which are 2 m1 plus 1, 2 m2 plus 1. There's also a reason why it is like this, which I can explain, but not during the course. And so here what you see is the T tilde m dqm plus 1/2 of the d tilde m1 m2 dqm1 dqm2. Okay. And this applied to the Airy curve. So this theorem, essentially it's in the work of Bertrand in 2011, which I mentioned this morning. It is somehow also in disguise in the work of Nicolas with Dunin-Barkowski, Chadrin, and Spitz, which I'm going to mention very quickly at the end. Here, this is a formulation which is a bit more recent, where one, I don't know, maybe that's my favorite way because it involves the less geometry possible, just algebra, to prove it. So you can ask the people, and some people here know about Airy structure, and so they would know how to derive this, so you can ask them. So let's try to put things together. We have one case where the partition function of a collection of class, which is just a trivial class, and the partition function of TR agree, provided you use this change of variable. You have an action on classes by translation and diffusion, which is realized by exponential of those operators acting on this. And you know what it corresponds to on this side. It corresponds to deforming spectral curve. So that does what we want. We just have to put the right normalizations due to this. So corollary. If I do Z d hat t hat of the trivial class is going to be Z tr of a certain curve that depends on d hat and t hat. Or you could say conversely, because I'm going to write what is a spectral curve here. And so to really see what is the correspondence, I mean, what do we need? We want the same operator here, but expressed in different variable. We want that to be t hat. That was a t tilde. We want that to be a t hat m dpm. And the two are related in this way. So you want that t tilde m is t hat m. And let's see in which direction this is. So some of this dO dpm divided by dO dqm. So it's like, because this is just a proportionality factor, this is like qm over pm. And qm over pm, it's 1 over 2m plus 1 factorial. And this is going to be the same for d tilde. This is d hat m1 m2 over 2m1 plus 1 to m2 plus 1. So if I really write in terms of spectral curve, what that means, here, this is Tm hat over 2m minus 1 double factorial, because that is a cancellation with that. And here, this is d hat m1, m2, over 2m1 minus 1, 2m2 minus 1. If m equals 0, by convention, minus 1 double factorial is going to be equal to 1, which is pretty clear in the way that that occurs here. Okay. And so then I can rewrite a bit differently if I want, is that the omega gn are going to be the sum of these integrals, the class, times psi classes, and then this 2mi plus 1 double factorial eta mi, gi. That's the equivalent reformulation of this. You've represented omega gn in terms of intersection numbers. And if you know the spectral curve, you can read these coefficients, d hat, t hat. Therefore, you can build a t hat of u, the generating series, and using this exponential formula, which I recorded over there, you have a nice formula for this class. Okay. In fact, these combinatorial factors, they can be nicely reformulated. And that's what I want to talk about now. It's Laplace transforms. So that was A, that was B, and C. So we have two things. We have, if we have y and omega 0, 2, we see that in order to get the t hat, for example, we have to get rid of these factors. So we want to introduce a linear map, which goes from formal series like this. So I'm actually going to put dz. And goes to C U, and that is taking Z. So what I am going to do, I'm going to apply that not to y, but to y dx. Dx being Z dz. It creates a little shift here. I'm actually thinking that here, whether I think I want a minus 1. Because if m equal 1, I should have a z, it should correspond to that. And that's what I want to correspond to. You add psi classes with a power 1. So m equals 0 would be a bit problematic. It's related to the shift that Rainier said. It would more or less correspond to move the branch point, the position of the branch point. So here I don't want to move the position of the branch point here. So I just start with, actually with 1. So this morning I said you can start with 2 for sure. So you have minus z plus something. If you start with 1, it amounts to change the coefficient here. For that, you have to use, it's a psi class to the power 1. And for that, you have normally the dilaton equation, which is quite simple, just multiplying by a factor. And so for this reason, you can actually, if you want to put an arbitrary coefficient here, you can. With what I said this morning, is continue to be well defined. But I simplified a bit my life this morning. So when I have this y and I multiply by dx, x is this square over the 2, so dx is z dz. I get a z2m dz, a bit like this. And this z2m dz, when it's divided by 2m minus 1 double factorial, if I want to get the t, so if I call this linear map L plus, and I put 0 if it's even. So what we want is that L plus of y plus z dx. And I define this L plus so that we have this. And if I want the d hat, if I apply L plus to the two variables of omega 0, 2, so what is the deformation? It's in this part. So it's omega 0, 2 minus omega 0, 2 standard, and I'm applying the same linear isomorphism. Yes? Yes. Here or over there? Okay. And this is the d hat. Okay. And then we have to do this kind of things. So we have to take the basis eta, but then multiply it by this factor which we would like to get rid of. So I'm also going to introduce an L minus, which is, so in the span, so maybe first I write for negative series. And L minus is going to send dz over, so dz 2m plus 1 double factorial z 2m plus 2 to what I will call Vm. And this space, it's isomorphic to the span of the eta as a vector space, because eta is characterized by its linear part, so I just throw away the positive part that defines the linear isomorphism. And so I want to send eta m times this 2m plus 1 double factorial to v to the power m. And then if I do that, I will have that L minus applied to each of the variable of omega gn. So I'm going to denote v1, etc., vn, the variable which I get by applying this map to each of the variable of the omega gn. And so here I will exactly get rid of these factors. And I get psi 1 times v1 to the m1, psi n times vn to the mn. So now we got rid of all factors. And this sum is nice, it's a geometric series. So I can rewrite it in a more compact way. Integral over mgn of the class divided by this. So once again, by dividing by a class, what I just mean that we have an nilpotent algebra. So I just expand that in geometric series. So this is the way this is defined. It's just much more compact to write it in this way. Okay. And that I will call that a local ELSV formula. So that's almost empty content compared to 5 minutes ago. I just gave name to these maps, removing factors. The point is that these maps actually have a nice realization in terms of Laplace transforms. So this is based on the following computation. So this is the z-plane. So the neighborhood of the branch point, which is here in the spectral curve. And I have the x projection. So here I have the x-plane. And so this thing gets mapped to here, the real positive axis. So the line I drew is the preimage of the real positive axis. And I'm going to consider the following contour. So I want it to be in positive orientation. So if I didn't do thing wrong, this is like this in the z-plane. So more precisely what this thing is going to be, it's a steepest descent contour. For x over u, assuming u is positive. Which means take the function real part of x over u and look at its gradient. It's a function on the spectral curve. And try to follow the direction where the gradient is maximal, so where you really increase the most, starting from the critical point, which is the ramification point. So slightly deforming, you would get something like this. And in the projection, this is called a thimble. The way to think about it is that you should squeeze that as much as you can to here, so you should squeeze that along the positive real axis. So I call that gamma. And this one is in the positive direction. And now here's the little computation that one can do. So if you integrate over gamma, dz over z to the 2m exponential of minus x over u. So more precisely, minus x minus xa over u. So x minus xa just z squared over 2. So it's dz z to the 2m exponential of something quadratic. So you can easily do that. It's a gamma integral. Just have to be careful with the orientation of the contour. And so what you obtain is that it's 2 pi u to the k, 2k minus 1 double factorial. So applying Laplace transform is exactly what creates for you this double factorial, because what you take the Laplace transform with respect to is this x, which is z squared. If you just did respect to z exponential minus z over u, you would get here a factorial. Since you do it with d squared, you get a double factorial. And then there's the other one. So this one I did the computation this morning. I hope my factors of 2 were correct, but it might not completely be. Is that what happens if you want to do the negative ones? So here I'm going to put, I change the sign and I put a v in the numerator. And if I'm not mistaken, you're going to obtain 8 pi v square root v2dk over 2k plus 1 double factorial. And so what I'm not totally sure is a factor of 2 and the global sign. But the rest is okay. Sorry? N? M, yes. Thank you. Here as well, so maybe let's change that for a k. Good.
Can I ask, I think I'm just a little confused about the contours. So gamma is actually the real line?
Yeah.
And what role does the other one play?
So this is the z-plane, and that's the map x, so it's essentially z squared over 2.
Right. And so you do that because when you compute that integral, you need to use the second contour.
So I'm computing, these are things on the spectral curve because they're a function of z. So it's here. But you could say, well, I express everything in terms of x, and this is now an algebraic function, just involve the square root. So then it means that you have to be careful if you want to write here what is the sign of the square root on both sides. It can be different, and that means that it's non-trivial. But the main point is that when u is positive at least, why do I choose this contour? It's because it's the only contour on which the Laplace transform is going to make sense, because then this steeper descent contour is defined so that the real part of x goes to plus infinity at infinity. So it decays.
Yeah, maybe I need to just write it in local coordinates to understand what's happening. But
So in that case, you can squeeze the contour to the real line. In that case, you can't because you have a pole here. Nevertheless, I mean, that's another form of the gamma, actually inverse gamma integral. That's essentially the Hankel representation of the gamma function. And we're going to play with that in the exercises. So that does exactly what we want here, that represent those maps L plus and L minus in a more maybe analysis way. That L plus of phi is going to be the integral over gamma of 1 over 2 pi u. Phi exponential minus x minus xa over u. And L minus of phi is 1 over 8 pi v. And then this with the opposite sign and the v in the numerator except of denominator. Okay. So playing a bit with this, you have the nicer form of what is the t hat and the d hat, or the t and the d attached to a spectral curve. So a bit of algebra. You find that, if I'm not mistaken, t hat of u, it's minus log of minus the integral over gamma dy exponential minus x over u, and then 2 pi u square root. Is that the t hat or t? I think that actually that might be the t. So the t hat was just essentially this Laplace transform, but there was this shift because we have y plus z, and then we had y dx. So what I say is that if you look at the transformation, the exponential form of translation, what you want is actually 1 minus t hat u over u. So the extra 1 essentially absorbs this guy, and the extra factor of 1 over u is absorbed by integration by parts, putting the d over here. Yes? Yes. I tend to forget, so I'm going to put it here. Thank you. So when you center here, it means that this is really when u goes to 0, it's really going to be a formal power series. Otherwise, it has exponential growth. So that's for the d. And then, well, the d hat. You would have this type of integral. I'm not going to write it. This type of integral in 2 variable for omega 0, 2. So if I just write it in terms of, okay, I'm going to try to write it. So normally you have to take this Laplace transform of so tilde means that you recenter with this. Normally you would take omega 02 minus omega 02 standard because you're looking at deformations. And if I want to put the omega 02 standard separately, I think what you're going to get is a minus 1 over u1 plus u2. So some of this has a pole because this guy has a pole at coinciding points. So this has also a pole when u1 is minus u2. And when you subtract it, this is regular, and this is the formal power series we want. Good. So now, good. So this is just another form of the theorem. And now I want to say a few words about what happens for more ramification points and what happens for global spectral curve. There's some little miracle that makes our life simpler.
So t we can just write as minus the logarithm of L plus of dy.
Minus the log of minus this integral. Which is L plus of dy, yes. Good. How am I doing with the time, Federico? Okay. Do you have questions? I think it's a good time actually to relax a bit and have questions before I write the more general thing.
All this that you said actually really works for the general variables D.
Yes. Yes. Exactly. And on the contrary, I'm going to specialize to the R matrix and say what is special about R matrices. But for TR, it doesn't matter.
And do you know, are there any axiomatic properties for something that used to be a cohomological field theory and then you apply the D thing? So does it preserve some nice property? You don't know.
Not the QFT axioms.
Yeah, that's clear, but...
I don't know what. It's a good question. And for example, typically you destroy integrability as well with the D hat. So.
And could you say the same for D? So can I write it also in terms of L minus perhaps?
D is still L plus. Because
still L plus.
what we extract
yes.
is positive is the holomorphic part. So to that we apply L plus.
Okay. But why
Yeah,
is there an 8? Or, sorry.
Yeah, thank
Sorry, I
you.
was just trying to figure out.
This is L plus.
So it would be some kind of, so it's L plus, so it's, so it's L plus tensor 2, and then you need to remove that bit, which I suppose corresponds to removing the standard part.
Removing this part.
Right. Okay, so these are actually the equations that you wrote there, and I just realized that. Okay. Thank you.
Okay, so maybe I need to rewrite again. Anyway. So now several ramification points, which is a kind of a little summary. So in that case, so let's call RAM the set of ramification points, it's finite. And instead of considering this algebra, we want to decorate it a little bit by A star tensor n. And A is the vector space with basis vector are are indexed by the ramification points. So nothing more than that. So it means you don't necessarily want to consider, you just don't want only cohomology classes, but you want to say, I insert vectors at the marked points. They're decorated by some vectors in A, so by some ramification point. And then you have a cohomology class. So if I have an element here, I need to choose some vectors. So for example, if I choose some ramification points, I can consider omega gn E alpha 1, E alpha n, which by abuse of notation, I'm sometimes just going to write omega gn alpha 1 alpha n. But you could also insert combinations of the E alphas. Good. So in fact, in terms of modular opera, this is also just tensoring by the endomorphism theory. And more or less, we can redo all the theory with that. So let's see if we can convince ourselves of that. So first, I said you can consider translations. In translations, you want to take the class and push it forward by the forgetful map of L points. But then you have to, for that to be a class, you need to insert some vectors. So T hat omega, Gn, you need to insert n vectors. So they are here, but then you have L. So before, what I was plotting was T hat of psi 1, etc., T hat of psi n. So n plus 1, in fact, n plus L. And then I was pushing forward. And T was some formal power series in the psi. So I was just inserting powers of psi. But now I also need to insert in these entries some vectors. So instead of taking T hat, which is just a formal series with complex entries, I have to take T hat of U, which is a formal series with vector entries. So what we really mean here is that you should take the tensor product on that and replace the U by the corresponding power of psi. And you multiply the omega gn n plus L, where you take the vector here, multiply it by its corresponding power of psi. So for the diffusion, it's a bit the same. Instead of taking the d hat which is a formal power series valued in C. So there was two variables, which correspond to the two psi class we put on both sides of an edge. And since both sides of an edge touch a vertex where we have the class, there needs to be a vector here to tell you which is the class you want at this vertex. So you want to take D, which is in A tensor A, formal power series in U1, U2. And then D hat applied to a class is going to be the sum over the stable graphs, 1 over automorphisms, the push-forward map, and then product at the vertices of the classes. So in the stable graph, some leaves, there are some leaves and some vertices, some edges, sorry. So here you have the vectors that you plot, which are here. But over there, what do you plot? Well, what you have to plot is the corresponding element of A coming from the D. If I pick a coefficient of, so U1, U2, so I have a certain pair of psi h and psi h prime, and the coefficient is the element of A tensor A, and I put it, there's one part of A belonging to that, one part of A belonging to that. Okay, so we have a similar action on classes. Then on the TR side, when you have several ramification points, now you don't have only one basis of differential form epsilon eta m. You have one for each ramification point. So if you have a spectral curve, you would take what do I want? Yes, so you're going to define eta alpha m. So you take a near alpha, near each alpha, you can take a local coordinate z, which depends on this alpha. And then you take the residue of the primitive of omega 02. So it's residue at, so here I'm going to be a bit sloppy because I'm going to make the confusion that I don't remember who said, maybe you said that was a confusion. Here, when I write z prime goes to alpha, strictly speaking, z prime is a coordinate, is this local coordinate. But since I want to distinguish between 0 for that local coordinate and the other, I'm going to call that z prime goes to alpha. So dz prime over z prime to the 2m plus 2. And how is that behaving when z goes to some ramification point beta? If this is alpha, same argument as before, it behaves like d0 z2m plus 2, because omega 02 has a double pole at coinciding points. And then there's some holomorphic part. If beta is different from alpha, well, omega 02 has no pole when one variable is near alpha and the other near beta. Therefore, you just have something holomorphic. That's why I put this delta function. It's Kronecker delta. And then the omega gn are going to decompose on that basis for the same reasons which I explained before. But now when we have to sum over these pairs of indices, So there's some numbers f, g, n, m1, mn, alpha 1, alpha n, and the eta alpha I, mi. So when we build the partition function, now it's going to be a function of h bar, but there's going to be a collection, I think it was of, I call that q. There will be q alpha m's. One collection of variables for each ramification point. And now what do? We expand y like this. So when, again, same confusion, expansion near the ramification point alpha in the coordinate z, so when z goes to 0. So here there's going to be some t tilde. So maybe I write directly with the normalization factors. So t hat, for this correspondence, alpha m over 2m plus 1 double factorial z to the 2m minus 1. And for omega 0, 2, now when z1 goes to alpha 1, z2 goes to alpha 2, you have the double pole if the 2 points you expand near the same point. And then you have a big sum m1, m2, and some d hat alpha 1, m1, alpha 2, m2, z1, 2, m1, z2, 2, m2. And this is, of course, up to the non-odd term. So you build the corresponding d hat and t hat. These are the coefficient of expansion. Oh, sorry, it's missing the factorials. So these are the coefficient of expansion in the basis E alpha um. And this is it. The only thing which is not clear, what is the starting point? I tell you how deformation match, but what happens if I set all of those equal to 0? So you have the Airy spectral curve with standard omega 0, 2. But so what is locally a spectral curve? You have vicinity of the ramification points, alpha, beta, and so on. And omega 0, 2, which is the only thing that makes things talk together, is 0 when z is here and z1 is here and z2 is here. So for d hat, t hat all equal to 0, you get independent Airy spectral curve, 1 for each ramification point. And then the omega gn, in fact, or maybe I can say the fgn's, there's no possibility that two copies of this little neighborhood talk to each other because of this. Therefore, this is going to be 0 unless all the alphas are equal. So, proportional to this. I guess this is a bad letter given the proportional. So, the same alpha. So it just means that your TR partition function, since there's no cross term when the alpha are different, is just the product of the partition function you have for Airy. So Z TR, I write Airy times ramification. This is just the product over the alpha. So that depends on H bar Q alpha M. And this is a product of the Airy TR for just the Q alpha M, but for M. Okay. So the theorem, we're just putting everything in what we did before together, is that if you take this d hat and t hat, which are elements here, obtained from the spectral curve, you're going to see that z of d hat t hat of what? Well, what I will write like this. So this is the class. And when I insert n vector, it's a class. If I insert exactly the same basis vector E alpha, E alpha, E alpha, this is the fundamental class. If two vectors are distinct, this is 0. And this is ZTR for S, depending on the Z d hat, t hat. With the same little combinatorial factors, so relation between the P's and the Q's. And this little thing about Laplace transform which I gave, if you want to explain d hat and t hat, you can do it by Laplace transforms, so this L minus and L plus, but now, since you have many ramification points, you have many of these steepest descent paths, one passing through each ramification point. And since anyway what you're interested in is formal power series in U, what really matters is just how that behaves near ramification point. You don't need to know how it extends to infinity. So it's also Laplace transform, but just first expand your differentials near a point, then apply this L minus L plus, and you get to the same formulation. So I repeated myself for this, but I hope this maybe you see better the structure also even in the one ramification point case. So this was as general as we can do for spectral curve which are smooth, have simple ramification point, and where y is regular. When the spectral curve has some extra properties, then this is extra nice. And it will slowly get us to the actual Givental formalism, which existed way before this, which is 20 years old. So first, I want to discuss what happened for global spectral curve. What you've seen in the course of Bertrand and TR is that you can compute locally, expanding everything near ramification point. That's TR only depends on that, and omega 0 too. But when there's a global geometry where your curve is compact, so what I will mean by global more precise is that the curve is compact, so the spectral curve is compact, so compact smooth, of course, and dx is meromorphic. So x and y in principle could have bad singularities, the essential singularities, and that's totally allowed in TR provided they are not at the ramification point. Essentially, whatever happens away from ramification points doesn't matter. But if you want what I call a global geometry, when actually dx is meromorphic. So x could have log singularities because then dx will still be meromorphic with simple poles. And omega 02 has poles only on the diagonal. So you may have been told, I don't know how Bertrand presented it, that omega 02 must have poles on the diagonal, but sometimes for some geometric problems you need something which has poles elsewhere. So this is also allowed in TR. So here I'm insisting that only poles on the diagonal in C cross C. So then there's a nice thing that D hat, which if you remember is this sort of Laplace transform of in a two variable of omega 02 minus the standard one, is going to be, so here I'm going to write things like this. Over U1 plus U2. And I will say that D factorizes. So in other words, the Laplace transform. So this shift was only due to the fact that you had this omega 02 standard. So this is, strictly speaking, the Laplace transform of omega 02 itself. And so you see it's this kind of factorized structure. So I'm going to define that. Laplace transform of omega 02 factorizes. And this is a lemma of Bertrand. And I wonder if, Nicola, you didn't have also something similar in your paper with Sergei. Yeah. Good. So there's this. I will say what is DOS afterwards, but I just did it here. Okay. So this also, because time is already running late, I was planning to prove it. I'm not going to do it, but maybe it will be an exercise. So it doesn't mean that you will have to do all exercises. It just means that you can choose which exercise you want to do, provided there's a suggestion from the set of people to a set of exercises. Okay. And so what is R and what is B dagger? This is just sum of E alpha, E alpha. And R, depend only on one variable, is the Laplace transform. So with a slightly different normalization, this one, 2 pi squared over U, exponential of x a over U, and as gamma b. So this guy, I want to see it as a matrix. So it has two indices, which are two ramification points. One of them is used for the cycle of integration. So here that should be B. And the other is used for which of the eta you're going to use here, and it's a eta B, eta alpha 0. So this is the differential form in that basis, eta, which is still defined here, which has exactly a pole of order 2 at alpha, plus some holomorphic part. And here there's a Laplace transform. Yes, I think it is like this. Okay. So this is an endomorphism of A, of this vector space. And here you have two copies, so the first copy acts on here, the second copy acts on here. And you have the sum over alpha. Good. If you remember, what was giving you a nice expression for the class was not really the t hat and the d hat, but the t and the d with these logs over there. So I'm going to write, when you have this factorization, actually you could say, well, this is true for a global spectral curve, but you could just say, imagine that you know you have factorization. I'm not sure this is equivalent to the globality, but imagine you have such a factorization. I'm going to explain just for rank 1, so one verification point, that this simplifies also quite a lot these formulas over there. So for A equals C, so in that case we don't really have to, this B is just, we can just say it's 1. There's no tensor product. It is this. So what becomes of D? So D, this was minus log 1 minus U1 plus U2 D. Actually, I don't remember it by heart. Yes, du1 u2 divided by u1 plus u2. So what do I see? If I write r of u, which is exponential of r of u, so the small r, which is the sort of normal log, then this thing goes here, 1 minus, I will have log of ru1, ru2. I take the log, I divide, so I get this. So it's pretty nice. I'm missing a hat here. Thank you. Okay. So just a little reminder. What this D was used for is that when you have D hat, T hat, then we're saying, we can write that as exponential of a sum of the T m kappa m. And then there was plus sum of boundary divisors and here we had this D of psi bullet and psi circle. So now it means that this guy is going to be a minus R. So it has this structure. And you see in the Hodge class, it was of this type. We had a Bernoulli number, so sum over m, Bernoulli number, and then psi bullet to the m plus psi circle to the m. So C Hodge class. So what I showed here, you can also write, it's a bit more cumbersome as well when A is higher rank. It's the same mechanism. So now I can come to some of the purpose of this talk. It's called chromological field theory. So I can finally define what is a chromological field theory. I think it was 4 co-FT. So there's one way to state concretely, a compact way to say what it is. It's an algebra over the modular operator given by the cohomology tensor this AN. But I'm going to expand that in formulas. So we're going to fix A, which is a vector space. So here you can imagine you start by 0. You don't know at all about topological recursion. And that's what people were doing in the 90s. That was introduced by Kontsevich and Manin. Because the type of property I'm going to write, they figured out it was the right type of property that would be true for classes coming from Gromov-Witten theorem. So from counting curves inside Kähler manifolds. So take a vector space with a pairing. And a co-FT on A. is a family of, so this class is when you insert vectors. And they should be, as we always wanted here, they should be symmetric when you permute the vectors, at least. Such that, so the slightly longer way to say, I mean, still short but longer way to say, it is compatible with the natural morphisms between the moduli space. And more precisely, so remember that we had this map beta 1. It was at the very start. So I'm going to draw again what it is. So beta 1 was going from mg1 n1 plus 1 to across mg2 n2 plus 1 to mg1 plus g2 n1 plus n2, and it was taking two stable curves with some punctures which have their own label plus the last puncture and attaching that together to form a node. And so when you have a collection of class, you can ask that this is somewhat compatible with this map. So what does make sense? You can take a class here and try to pull it back. So you would have a class on G1 plus G2, N1 plus N2, and of course you should insert, so maybe I will write things like this. W1 tensor W2. This is the list of all vectors you insert at the first N1, and the list of all the tensor of all vectors you insert here. So and so this is indeed a cohomology class on this moduli space. Now I can pull it back. When you pull back, you get a cohomology class on this product of moduli spaces. We want to say it's compatible, which means that, oh, what other class do we have here? Well, we have a class which is omega G1 N1 plus 1 with W1. And well, I have to say what I insert here for the last point. Tensor, because the cohomology of a product is the Cartesian product is the tensor product of the cohomology. So N2 plus 1. And here W2. And here I have to say what do I insert. Good. So I could ask, I mean, whether it's true or not, it depends on your omega. I could ask that when I pull back this, I should exactly get this. But what do I put here? What is
Again, with the action of Sn, you have an action of Sn in the entries of the tensor product and an action on Sn on the marked points, but like it's an action of Sn times Sn. Okay.
You still have 10 minutes, Gaëtan.
So now it should work better, I hope, for the people online. Okay. So I start again. So summarizing what I said in the last 5 minutes, I just explained that a co-FT, possibly with a unit, is a family of class satisfying all of these axioms, which is a natural thing we can formulate given the algebraic structure we have on the cohomology ring. Whether that exists or not, it's a different question which I'm not going to discuss. Okay, but imagine you have a co-FT let's look what it induces just on the simplest thing, which is 0, 3. So M03, the moduli space of Riemann spheres with 3 punctures, where there's only one up to automorphism sphere with 3 punctures, because you can always fix using a PSL to see element points to be 0, 1, infinity. So this is just a point. So the cohomology is rather simple. And we have this omega 03, which is a map from A tensor A to C, which is this cohomology ring. So it's a trilinear map. It is symmetric. And you have a pairing on A from the start. Therefore, you can put some A on the other side using the isomorphism between A and A dual that the pairing induce. So you can induce a map from A tensor A to A, which I'm going to call mu. And now it looks like a product. Take 2 elements, you get a new one.
Don't you also need some addition on omega 03 with like a unit with the unit axis? That it gives the metric?
Let's assume it. I'm not sure one really needs it. You may have Frevenus Algebra without a unit.
If you had a co-FT with a unit, you need another axiom, right? Which is that omega 03 of
that's true because we don't have moduli space which are unstable. Yes. So if you have a unit, you need plus omega 03 of V1 tensor V2 tensor 1 is going to be the pairing of V1 and V2. Yeah, thank you. So you get this, and because of symmetry, this is a commutative product. And then you can look what happened when you degenerate a sphere with 4 punctures and look in degree 0. You're going to see this guy actually must be associative. So that's using beta 1 for 0.3 times 0.3. Good. So the commutative associative product, you have this pairing, and the two are compatible in the sense that the omega 03 is represented in this way. So this is called the Frevenus algebra. And this is equivalent to the data of a two-dimensional topological quantum field theory. Also, I won't define exactly what this is. You may already have heard about it. Okay. So here are the other two quite deep results. This explains why these things are interesting in geometry, and which the theory of topological recursion doesn't justify. On the contrary, you rather use deep theorems in mathematics and you play with it to obtain new interesting things with topological recursion. So this is the first one, is that due to Givental, just for the restriction of genus 0, and to Faber, Shadrin, and Zvonkin, so this is about 20 years ago, this is about 15 years ago, maybe a bit more. In general, that, okay, we have all these actions on classes. So what if we start with a co-FT and we act by D by translation and diffusion? Do we get a co-FT? The answer is no in general. But if you have that D of U1, U2 factorizes, so it's more or less of this form for some R, then omega co-FT implies D hat omega co-FT. And you can actually do a T if you want. But if you want omega co-FT with unit, if you want to preserve the unit, so perhaps I should write. That was the first part. If furthermore T of U is U identity minus R of U applied to the unit. It's a very specific form for the T hat matrix. Then this also preserves co-FT with unit. And so if you have here with unit, then you would also, yeah, well, maybe I write separately. If you just apply the D, it doesn't touch the unit, then you still have it here. But if you start to turn on some T, you need it to be related to the D hat so that when you compose the two, you still get something with unit. Okay. And then the theorem 2, which is even more marvelous, and which is due to Telemann. And this is telling you that if A as an algebra is semi-simple, which means that as an algebra it's a sum of one-dimensional algebras. So you have a basis of vectors so that when you multiply 2, you obtain the same up to scale. It's not clear that, that doesn't always exist. But if that exists, you say it's semi-simple. Then there exists d hat factorized, so there exists an R. I can directly talk in terms of R because I want to apply this theorem with things of this type. And T so either T specified by R because you want to preserve the unit, or just T is arbitrary, so I would say T. So that, and here I'm simplifying a bit the statement. There's a further transformation psi which is not too important for us. But when you apply, so what I will call D at R, so a D obtained from this, and then T to, so what do I put here? I'm going to take the restriction in chromological degree 0 of the omega. Then you reconstruct the full omega. So together these things tell you that if you have any coeft on a semi-simple A, essentially you just need to know the degree 0 part. And the degree 0 part, I don't have the time, if you will take 5 more minutes, in fact is determined by this Frevenus algebra structure. So it's something quite easy. It's almost linear algebra to know it. Sorry? Chromological degree 0.
Genus?
Arbitrary. So that essentially only contains info from the Frevenus algebra. Then you would find a T hat and a D hat which reconstruct the full class. So either you say, well, there's not so many semi-simple coeft, or you say, well, that's great, actually, I know lots of semi-simple coeft, and that's what happens. Therefore, you can reconstruct it in this way. And since you know, that I didn't say, but this is not too far from just a sum of trivial classes, you can apply TR for this, so you can deform spectral curve, and to any semi-simple coeft, you can find a spectral curve that computes exactly this. And that I would state as a corollary, otherwise, yes?
And then all of these things with the general case and then Telemann stuff, the connection with the spectral curve are just for those that they have this omega 02 with the poles?
Not necessarily. So I say it's an implication. If you have a global curve, then you have a factorized thing. But if you have a factorized thing, then the correspondence I gave gives you at least local spectral curve, which you can use for TR. Whether it's global or not, I didn't say. There's some work of Nicolas where he tried to analyze if you have a start from a semi-simple coeft, whether you can really construct a global curve, and sometimes yes, sometimes no. So here I will state that as a corollary, but it's really a non-trivial work, and the first people to do it were Nicolas, so it's Dunin-Barkowski. Orantin, Chadrin, and Spitz. And somebody recognized, so this thing is called Givental theory. And they recognize a similarity between, they establish a dictionary between Givental theory in a semi-simple case and topological recursion. So maybe I can put like that, semi-simple co-ft. To a semi-simple co-ft, you have an R and T. And to that, you can attach a spectral curve. So that by TR, you get a collection of omega g n's. Here, you get the partition function of your co-ft. And when you expand these two things, so here I could say I get to the TR partition function. And then I get an equality. So once you know the R and T matrix, it's rather explicit to get a spectral curve by this Laplace transform. Okay. So I think in the title that proposed at the beginning was Givental theory. So I didn't really explain why Givental did this. So that I can say in, yes?
Just the first comment. Yeah, if you start from a semi-simple chromological field theory, just to precise, and it's related to the question before, that in general, you don't know whether there will be really a compact spectral curve.
Yeah, so it's a local spectral curve. Just specify expansions. You don't know whether there's a global curve or not, indeed. And that's an interesting question, on which Nicolas and Paul and Sergei worked, and I don't remember who else. Maybe Maxime Kazarian was also in the paper. It's a modular subset of co-authors. PS or Popolitov? Okay. So this is going to be really quick, but Frevenus algebras, you can try to deform them. So you would have family of Frevenus algebra, and the right notion for that is the one of Frevenus manifold, which was invented by Dubrovin. And you said semi-simple, so essentially the Frevenus manifold M, it means that you have a family of Frevenus algebra structure on the tangent spaces. But then there's extra conditions, so I'm not going here to define Frevenus manifold. That would take, I guess, 2 more hours to really explain. But think of it as a nice family of Frevenus algebras. And from this, in fact, the product and the pairing, everything is encoded into a function called the prepotential. Which has lots of, first, geometric information, but also lots of physical information. For example, that contains Gromov-Witten invariance in genus 0 when you have a Frevenus manifold coming from Gromov-Witten theory. So that's really the thing that you really want to know, actually to specify the Frevenus algebra. You just need to specify this plus a few other things. Okay. And in the semi-simple case, so the problem was really to determine this F0 everywhere. And you can do it somehow when the thing is semi-simple, and there's a few more assumptions here which I'm not going to write. And what Givental said is that actually what you can do, that you can attach to a Frevenus manifold a certain class. And you do it by deforming essentially the collection of trivial classes with this specific transform that preserve co-ft. So essentially, I mean, he really wanted initially thing with unit. So with T and R satisfying this, and then the D hat is related to R by this way. So you can get a certain class. So if there's one more transformation, which is just a change of basis, correspond to change of coordinates here as well. So don't want really to talk too much about that. But you have something like that, more or less. And then what's the purpose of that is that you can look at the partition function and just in genus 0. At the time of Givental, he only knew that this action preserved co-ft in genus 0. So you just do at omega 0 n. And so you look at the coefficient of h bar inverse in log of this partition function. So these are intersection numbers. And then the claim is that a certain restriction of this, so to finitely many variables, so that's a restriction, was equal to the F0. So we could reconstruct by means of constructing these R and T, and these R and T you can actually construct it from the structure of the Frevenus algebra, not knowing the F0. And in this way you could represent, you could get back the F0. So that was Givental theorem, which you apply to Gromov-Witten theory. And all what we've seen today is a shadow of this in TR, where the space of deformation is in fact much bigger. But in particular, it applies to this particular case. And it's a bit frustrating, but we are still pretty much stuck to the semi-simple case, which is annoying. If you do general Gromov-Witten theory on compact Calabi-Yau, it's not semi-simple. And you could say, well, but still, I have an action-preserving coeft. Yes, but here this thing is stating that for semi-simple, this is more or less transitive, this action. You can reach any point from the trivial one. When it's non-semi-simple, there's really no hope that something like that is true. You just get a very small subset of non-semi-simple coeft when you act on a given one. So that's about where even true geometers stand for now. That's all. Let's go to the beach.
Questions? Yes. Okay. So he's closer.
Could you remind us what psi is just at the beginning of the formula and the second?
Yeah, that's the thing I didn't want to say about.
Oh.
But it's, so at least here, imagine it's just a change of basis that go from maybe the basis you started on A to that particular one where the two vectors multiply to a multiple of each of them.
But if we want to be slightly imprecise and we remove the psi, this is still saying that more or less omega is obtained from the degree 0 part by a Givental.
So you just need, it's just too restrictive. I mean, essentially, you have to do this isomorphism if you start from a thing. And the psi is just the obvious thing which just does this little change of basis.
Okay. But psi is incredibly simpler than D and T.
Absolutely.
It's, okay.
So now it's the action on the A tensor n part of the modular operator.
So Gaëtan, we have this bigger family of transformations that in general do not factorize. I don't understand what you attached to the legs, so the half edges where the marked point used to be.
So that's the thing I a bit swept under the carpet. If I was quicker, which I probably shouldn't anyway do, I would have explained that. So far, I gave you this local, what I call local ELSV, and it was more or less when I expanded on the eta basis. You could also expand on a different basis, which is the psi d basis. So, well, just names I give to it, but I think Bertrand called it psi and psi hat. But essentially, what you do that if m equal to 0, this is just eta. But when you have a global geometry, the natural thing to do is you can apply d over dx. And you differentiate. You don't get the same, sorry, not eta, but psi. So you define it by induction. And in general, this psi m is different from the eta m. It's a change of basis. So when you do a change, and so the nice thing is that when you do Laplace transform, doing this is more or less multiplying by u or dividing by u. So this is quite nice in Laplace transforms. Therefore, if you rather expand omega gn on the basis of psi's, you end up getting an extra factor for the leaves, which is responsible for this psi I. For example, in the Hodge formula, in the GRR, I had this sum over psi I to the m and some Bernoulli numbers, which I totally discarded. I mean, I just said you take the action on one and then you multiply by this exponential. So I'm saying that this actually can be absorbed in a change of basis of decomposition of the omega gn. And so what you get, this factor of psi, is anyway going to be r. So I hope. That's what comes in my head right now. I didn't do the computation. I think it works like that, but maybe Nicola can contradict me if it's wrong. So what you get is the factor, little r, which is still defined, that you can always do, as so psi 0 or the Laplace transform of psi 0 or eta 0. Because then the Laplace transform of the psi k are just going to be given by that multiplied by u or divided by u. So this is the factor you will see in this exponential of sum of Tm kappa m, and there's going to be plus sum of r psi I, something like this when you expand in this basis.
I see. So this lemma in particular says that when it does factorize, then you get that r coincides with the one that comes.
Yes. And the only thing when it doesn't factorize that, okay, you do have this r for here, but it has nothing to do with the d hat. R essentially du0 more or less.
Yeah, that's what I wanted to say. In general, even if you don't have any factorization, you've got a weight associated to the leaves, which can be computed in terms of the coefficient d, which are there. It's just that you might not have a simple representation.
Somehow you still have an r, but it's just not doing what you want for the weight of edges.
Okay, no more questions?
If you act by a R and a T matrix on a semi-simple co of T, will you always get a semi-simple co of T?
Yes.
Okay.
Because, let me see. It doesn't change, is it correct? It doesn't change the degree 0 part of the cohomology. It's the same Frevenus algebra, apart maybe from the change of basis.
Also, it's because you want in the basis where you algebraize.
Yeah. So apart from change of basis, which is just an isomorphic Frevenus algebra, the reason is that what you do with this action with R and so on, you just sum or stable graphs, which are codimension and positive codimension except for the top term, which is your original class. When you just look at degree 0, well, essentially it's determined by the degenerating the curve totally to a pair of pans. So you don't have room for any of these actions. So it doesn't change the TQFT.
No more questions? Okay, let's thank Gaëtan again.